Dear professor, my name is Nguyễn Xuân Tung. Today I will present my final report for the subject unmanaged aero vehicle application. So the presentation will include four parts: system model, problem information, solution, and simulation result. The system model I have present in the midterm, so I will briefly talk about it. Mm, so we can see that we have an error of communication. The base station will serve all user, however, some user is far from base station. So to deal with this problem, the the system will provide an UAV to serve user far from base station. So it will cause the interference between communication between UAV and user served by UAV and user served by base station. We have the time slot, time resource. So all of user served by station will use own time resource, but user served by UAV will be divided into different time slots. So it means that user served by UAV will not interfere each other, but we have to control and manage. We have to manage the time slot allocation for communication between UAV and user far from base station. I mean user served by UAV. So the system model, I will present is a signal model between UAV and user. I have present is a midterm, so I also will briefly talk about it to explain for the problem formulation. We have the receipt signal from UV will have three parts. The first part is a design signal from UAV, and the second part will be interference from base station to UAV. It will be represented by a certain interference parameter in simulation result, and the third part, the final part, is a thermal noise. So the channel between UAV and user will be I only consider the path loss with the reference channel power gain from UV to user will be represented by rho, and the power from UV to all user at every time slot will be represented by will be equal, and is a P. In simulation result, I will allocate 20 milliwatt to 20 milliwatt is the power for communication from UAV. So we can calculate the achieve rate of user. It will be managed by an integer variable time slot allocation SIN. N will be index of time slot and I index of user. We have I, capital I, very small I, sub p is the interference from base station to user served by UAV. So we will have the problem formation is to maximize the achievable rate with variable of time slot and trajectory W. W is will present for the coordinate of UAV. We have the first constraint is achievable rate constraint. The achievable rate of user have to larger than a threshold, and the interference from UV to user served by base station will be smaller than a certain interference. The constraint 3D and 3E constraint about movement of UAV. It have to be circular. It have to be closed in I mean that's the constraint 3D. The UAV have to move to the first location, and the 3E the constraint about the maximum distance movement of UAV. The two last constraint is constraint about time slot allocation for each user served by UAV. So we can see that this problem is non-convex optimization problem. To solve this problem, at first, to deal with mixed integer non-convex problem, I will relax the variable of type slot into continuous one from 0 to 1. However, this problem is still hard to solve. To solve this problem, I will iteratively solve each one variable. At first, I will fix the location of UAV and solve time slot allocation. Then fix time slot allocation and solve the trajectory optimization. So I will iteratively solve this problem until it converts to a certain value. At first, the first subproblem for time slot allocation, because after we like time slot allocation to continuous variable and with and given trajectory. So this problem with constraint about achieve rate and time slot it is a linear of the program problem, so it can be easy solved by Civic. The second subproblem is the problem about trajectory with constraint about achieve rate and the interference from UAV to user server by base station, and the constraint about trajectory constraint about the maximum distance movement. So this problem is non-convex problem. We have the achieve rate of X user is non-concave on W, but it is convex over the norm of distance between UAV to X user. So I have the proof about convexity. I apply the first order Taylor expansion. The about achieve rate of X user will be represented by the inequality 8. So with X and Y will be present by the equation 9 and 10. The constraint should be equal to the inequality 11, and the constraint 60 will be represented by the inequality 13. So the problem of trajectory will be represented again by will be transformed approximate to the problem 14. So this problem can be solved by Civic, but when I solve this problem, the Civic will reject the norm of distance. So I will use the sum of power of distance to present for the vector of UAV, a vector of distance between UAV and user. So I will solve the alternating optimization algorithm with given. At first, I will initialize the trajectory and denote the index of iteration equals 0. So I will repeat soon the time slot given the trajectory from the previous iteration, and then solve and find the optimal trajectory given the time slot. Because both subproblem I can find the optimal, so it means that when I solve one and fix as a variable, I always can improve the optimal value of total sum rate. When the total achieve rate of all user cannot improve certain percentage, I will stop the algorithm. So here we have the parameter set up. The important thing is the last three criteria. It is about the initial trajectory. I will use popular initial trajectory. It is a circular trajectory with the central location of all user and with radius is minimum about the movement or the distance from user to the center. And I will use the epsilon to stop e so 0.001. It means that if the total achieve rate cannot improve more than 0.1%, the alternating algorithm will be stopped. So we have the simulation result compared in three scheme. Is the three scheme different of the maximum interference from UAV to user served by base station. When the maximum of interference from UAV from to user served by station, like it means that the UAV cannot fly near the user served by base station, but the UAV always try to move around and try to move over the user is served. And for all case, the total achieve rate of all user always larger than 7.7 bit per second per hertz. So the final figure I saw the achievable rate of the total achievable rate of all users served by UAV versus time the total time resource allocated. So when we increase the time, the total achievable rate of user will be increased. But in case the trajectory of UAV is circular trajectory and the even we increase the time resource, if we do not optimize by optimization, so the achieve rate of user will not improve. So for each point in this figure, I run with 1000 realization. So it's in my reference for this presentation. Thank you for watching, Brazil.